when I come to work every morning. What excites me are really the new possibilities. In my group, we ideate and play. We work with solutions, we work with gases, we are reducing materials, we are oxidizing materials, we are transforming the metallic states, we play with solubilities, we play with pH conditions, we manipulate matter. The beauty and the creativity of what we do is then translating some of these pathways that we develop for wide ranges of applications, including energy and environmental security, as well as climate security. I'm Greeshma Gadikota. I'm a professor at Columbia Climate School. I'm trained as a chemical engineer, and a lot of the challenges that I address are in the area of energy and environment. My earliest work involved working with large quantities of CO2 emissions and turned that into calcium carbonate, which then we could use as building material. Nature does a fantastic job of complexing metals in a solid carbonate state. As an engineer, I try to understand how nature does it, and I get those processes to go fast. And the key challenge there is actually the solubility of CO2. So the approach that I developed involved CO2 that's in the flue gas or in air, concentrating that CO2 in aqueous solution to produce high purity calcium carbonate. We came up with various ways to get those reactions to go fast. Then we started to think about, okay, maybe can I do this to the order of tens of grams? And then we moved to hundreds of grams and then kilograms. And at this point, we are working towards commercialization of that technology. All of these materials that we are throwing away or landfilling, we need them. Maybe these materials can be used in semiconductors. Maybe they're needed in my cell phone. So one example would be, if I take an alkaline residue, this is a slag that comes out of iron and steel processing, a material like this can have up to 30 to 40% silica in it, which would otherwise perhaps be landfilled. We could refine it, put it through a series of chemical pathways, and get it to its desired end products, such as for solar-related applications. And now, we've also worked on rare earth elements. Now, rare earth elements have a wide range of uses. They're used in magnets, many applications. And being able to build up a domestic supply of these materials is actually really important. And for that reason, we are interested in being able to develop new chemistries for extracting these materials. We are acutely aware of the timescales that are needed to achieve energy and climate security and sustainability. Commercialization is a very important consideration for us. We think about these elements in our day-to-day work, how a mining company's CEO is thinking about the value of their resource and assigning value, to how a startup might think about deployment, to larger considerations around geopolitics of metal production if we go to scale, arranging the financing for it, right? And all of this knowledge resides in this wonderful entity that we call Columbia University. The solutions that are needed for energy, environment, and climate security can all coexist together. It's really the ability to take a fresh perspective and a fresh look at problems every single day. And that, for me, is the most exciting part.